Alright, so for this one, we're asked to write the ion product, or the KSP expression, for the sparingly soluble salt barium fluoride. Of course, the formula for that is BaF2. If we're talking about solubility equilibria, we always write the equation for that sparingly soluble salt being a solid. That's on the left of the arrows for equilibrium. And then, of course, on the right, we write the ions which are produced. On the right, we always have the aqueous phase ions. In this particular case, we'll make one copy of the barium 2+ ion. We're also going to make 2 copies of fluoride, F- aqueous. And hopefully we study really good so we don't get the F- on the exam, right? Now the KSP expression is nothing more than the equilibrium constant expression for this reaction. So we go to molarities for these aqueous ions. So I write the square brackets, and I have my molarity of barium 2+ and my molarity of fluoride F-. And again, don't forget, you got to put this 2 up here because of that 2 in the stoichiometry, right? Now for a normal equilibrium constant, you would divide by the reactant, which is BaF2 solid here, okay? And you'd put a molarity term in the denominator. But of course we don't do that here. We don't need to. Reason being is that solids don't appear in equilibrium constant expressions. So we basically just erase that part of it. And again, it's a nice thing about solubility equilibria, because whatever is on the left of the arrow is always a solid, and it does not appear in the equilibrium constant expression. So that is our answer for the KSP expression. So that's pretty basic stuff. Everybody needs to know how to do that to work the more complicated problems, okay? Now the second half of this problem asks us about pH, and this is kind of a different concept, okay? It's about the pH affecting the solubility of the barium fluoride. Now in some cases, changing the pH may affect the solubility of our sparingly soluble salts. Which cases will it affect the solubility, and which cases will it not affect the solubility? My cat is enjoying this problem. Okay. So let's take a look at that. Oops, it's not going to work. Let's take a look in cases where it will affect the solubility and where it will not. Now in the case of barium fluoride, the pH will affect the solubility. Let me explain why. The F- anion, fluoride, can react with H+ to set up a separate equilibria in which we generate HF, aqueous. Now HF is one of our weak acids, isn't it? So if we try to dissolve the barium fluoride in a solution which is very acidic, what that means is that there's a high concentration of H+ in acidic solutions. That's going to push our equilibrium to the right. And in other words, once this barium fluoride starts to dissolve, the fluoride ion which is produced can react with the H+ to make this weak acid. This second reaction then is a means by which we can remove or bind up the fluoride ion. We remove it from solution. And if we remove the fluoride ion from solution by this second reaction, that's going to make our salt barium fluoride more soluble. So I would expect barium fluoride to be more soluble at low pH, where we've got a lot of H+. And the reason why is this second equilibrium right here, where we can bind up the fluoride by making the weak acid HF, okay? All right, now we're also asked to compare and contrast this case with barium chloride. If you read the problem carefully there, it seems like they're suggesting that the barium chloride is not pH dependent in terms of the solubility. Can we explain why that is? All right, well, if we're thinking about barium chloride, I got to erase all this stuff now, right? We could write a KSP expression for barium chloride in the corresponding equilibrium. That's no problem. We just have BaCl2 solid, equilibrium arrows to make what? Ba2+, some chloride comes along here for the ride, 2 copies of that. So why couldn't you propose the same type of reaction? I mean, it seems like the chloride might be able to react with H+, setting up a equilibrium. And if we do that, we're going to form HCl aqueous. Oh, now this is a problem, right? Look at what we made. We made HCl aqueous. We know that that is on our list of strong acids. Hydrochloric acid is a strong acid. It exists as what? 100% dissociated. So will this reaction proceed to the right at all? Are we going to make any HCl? No, we're not. This equilibrium lies far to the left. And as a result, it does not take off at all. And because of that, there is no way, no means to sequester away or bind up this chloride anion. This reaction doesn't happen to any extent. And as a result, lowering the pH is really not going to have any effect on the solubility of this stuff, okay? So you really need to look for